Assalamu alaikum. It's Ahlam Deep, and I'll be explaining Chapter 2, Rate of Chemical Reaction, Part 1. Before we start, please prepare your stuff. By the end of this video, please check if you have acquired the following objectives. From previous years in chemistry classes, you already learned about chemical reactions. In a chemical reaction, molecules collide with each other, so bonds are broken, new bonds are formed, and reactants are converted into products. Chemical reaction might be slow, as the ripening of an apple or rusting, or it might be fast, as fireworks or formation of precipitate. So, not all chemical reactions occur at the same speed or rate. The evolution or the progress of different chemical reactions is not the same. But how is this rate or progress measured? How do we know if a reaction is fast or slow? This is related to the time taken by the reactant to disappear and products to be formed. Reactants can disappear and products can be formed in only few seconds, or it might take them a longer period of time, 5 hours, 3 days, or maybe many years. A branch of chemistry called Kinetics aims to study the progress of a chemical reaction with time. In this simple chemical reaction, a reactant A produces product B under specific conditions. During this chemical reaction, the number of particles of A in purple decreases with time, while that of B, which is a product represented in green, increases. Now, let's fill a conversion table for this simple chemical reaction. At time T0, there were 16 particles of A and 0 particles of B. At 8 minutes, there are 8 particles of A and 8 particles of B. At 15 minutes, there are 4 particles of A and 12 particles of B. At 23 minutes, there are 2 particles of A and 14 particles of B. At 30 minutes, there is only 1 particle of A and 15 particles of B. We notice that at each instant T, the number of particles of A consumed is equal to the number of particles of B produced. The evolution of the reaction is minus X for A and plus X for B. So, at the end of this reaction, X reaches its maximum value, which is equal to the initial number of particles of A, 16, and at T final, the number of particles of A is 0, and that of B is 16, equal to the initial number of particles of A. Filling this table is a piece of cake, isn't it? But what if the reaction becomes more complicated? Let's see. In this chemical reaction, A plus 3B gives 2C. This means that 1 mole of A reacts with 3 mole of B to produce 2 moles of C. We have a mixture made of 10 mole of A and 30 moles of B. Pay attention that in this reaction, the mixture of reactants is stoichiometric. We can know by simple look to the initial number of moles. 10 and 30 are proportional to the stoichiometric coefficients of A and B, which are 1 and 3 respectively. The evolution of this reaction can be represented by minus x for A, minus 3x for B, and plus 2x for C. Let's say that at t equal 10 minutes, we find that there are 5 moles of A. This means that 5 mole of A remained. So the number of mole of A reacted out of 10 is also 5. So x is equal to 5. To calculate the number of mole of B remaining at the same instant, we have to do the difference N initial minus N reacted. 30 minus 3x equal 30 minus 3 times 5 equal 15. To know the number of mole of C produced at the same instant, we should calculate 2x. 2x equal 2 times 5 equal 10 mole. At t equal 20 minutes, let's say that N of A equal 3 mole. So the number of mole of A reacted is 7 mole, since 3 mole remained out of 10. So x equals 7. Now, the number of mole of B remaining at t equal 20 minutes will be 30 minus 3x equal 9 mole. And the number of mole of C produced will be 2x equal 14 mole. Now, at t equal 30 minutes, there is only 1 mole of A left. Please pause the video and take 1 minute to fill the table for t equal 30 minutes. Your answers should be equal. Now, at the end of the reaction, x will be equal to 10, which is the maximum value that can be reached. Since the mixture of reactants is stoichiometric, both reactants, A and B, will be consumed totally. Their final values will be 0, and the number of mole of C at T final will be 2 times 10 equal 20. If we go back to the table, we see that the number of mole of A and B are decreasing with time. So I can draw a graph representing the variation of the number of mole or concentration of a reactant as a function of time. I will obtain a descending curve that reaches the x-axis at the end of the reaction. On the other hand, the number of mole of C is increasing with time. So the graph representing the concentration or the number of mole of a product as a function of time will be an ascending curve that tends to a horizontal asymptote at the end of the reaction. These red curves are called kinetic curves. To sum up, the rate of a reaction can be determined by the rate of disappearance of reactants or the rate of formation of products. By analogy to physics taken in grade 8 and grade 10, when we talk about rate, we have to specify if we are talking about average rate or instantaneous rate. Dear students, this is the summary of this video. You have to write these main ideas on your copybook. And you have, as a homework, number 1 and 5, page 45 of your book. Before ending this video, I'm going to give you some tips about your homework. For number 1, page 45, please pay attention to the stoichiometric coefficients of the reactants and the product. For number 5, construct a conversion table made up of 3 rows, one for T0, the second for the evolution, and the third for T final. Don't forget to check if the mixture of reactants is stoichiometric or not. Finally, this is your agenda. See you soon in the next video. Wassalamu alaikum.